In this talk, we present Class-Incremental Domain Adaptation, a joint work done with my co-authors at the Indian Institute of Science. We first introduce the motivation for the problem setting. Machine learning models commonly face two challenges. Firstly, they yield suboptimal results when there is a domain shift between the training and the test data. Secondly, once a model is deployed in the real world, it misclassifies unseen objects since its recognition capabilities are limited. Therefore, it is essential to upgrade the model for the chosen target domain once it is trained on a source dataset. In many scenarios, it is difficult to obtain labeled samples from the target domain. Therefore, unsupervised domain adaptation methods have been proposed, where a labeled source dataset is used along with unlabeled target samples to adapt the model for the target domain. Most commonly, closed-set domain adaptation methods assume that the source and the target domains share the same categories. They adapt the source-trained model by aligning latent representations between the two domains. Thus, the source classifier can be reused for the target domain. However, the closed-set assumption is impractical in the real world, where a typical target domain would contain samples from additional unseen categories which are not observed in the source dataset. This issue is tackled in open-set domain adaptation, where such unknown target samples are rejected by the classifier by assigning a separate label called unknown. But this introduces a second challenge. Note that the target samples with diverse semantic content are clustered into a single unknown class. This process disturbs the semantic granularity of the latent space, and the model is unable to perform a fine-grained recognition among such samples. Therefore, while the model detects these samples as unknown instances, it cannot be upgraded further to recognize novel classes. We argue that the model must also recognize these new target categories to improve its generalizability over the target domain. For example, here the model should recognize the bottle and the bookshelf as separate categories rather than discarding them as unknown. Such a model will have more practical use cases. Furthermore, unsupervised domain adaptation methods require the coexistence of the source and the target samples. This is again an impractical assumption in the real world, since the source dataset may not be readily available while upgrading the model for the target domain. Thus, we must study methods that can upgrade the model in the absence of the source dataset. We find in the literature that certain class-incremental methods are source-free in nature and only require samples from the novel target classes. However, these methods require labels for these samples and usually do not consider the domain shift. To summarize, we draw motivation from the literature to study a practical scenario which we call class-incremental domain adaptation. While upgrading the model for the target domain, we aim to tackle domain shift. Motivated by unsupervised domain adaptation methods, we assume that the target data is unlabeled. Moreover, since the source dataset may not be readily available during the model upgrade, we aim to perform adaptation in the absence of the source dataset. Further, we aim to achieve a fine-grained recognition among the novel target classes. For this purpose, we assume access to a single example from each new class. This can be seen as the knowledge of the classes that must be added to the classifier during the model upgrade. Our approach is divided into two parts. First, a foresighted training is performed on the source domain to ensure that the model supports a source-free upgrade in the future. To achieve this, we use a prototypical networks-like framework to augment the model with out-of-distribution detection capabilities. Then, to upgrade the model for the target domain, we learn a target-specific latent space, which can learn class semantics that are suitable for the target domain. Here, the domain shift is reduced by aligning target clusters into appropriate regions using trainable guides. First, we look at the foresighted source training. The network consists of a CNN backbone FS and a classifier GS having an additional class to model the out-of-distribution regime. The idea is to learn compact feature clusters for the source classes which can then be approximated using Gaussian prototypes. These prototypes will capture the source semantics in the latent space, which can then be used during the source-free model upgrade. We define a class-specific Gaussian prototype as a Gaussian approximation obtained using the source features for each class. These Gaussians pertain to the regions in the latent space where there is a high density of source samples. To improve the reliability of the Gaussian approximation, we impose a log softmax loss on the Gaussian likelihoods of the source features to increase their affinity towards these Gaussian prototypes. Further, we aim to capture the low source density region as a negative regime which can accommodate novel target classes. To this end, we introduce a negative class in the source classifier and obtain negative feature samples that are beyond the 3 sigma bound of each class-specific Gaussian. Therefore, the network is trained using both source samples and negative samples. Finally, we expect the Gaussian prototypes to model the semantics of the source classes. Note that the Gaussian prototypes are cheap and can be stored along with the model parameters in contrast to the source data. This enables a source-free upgrade in future. To adapt the model for the target domain, we begin by learning a separate semantic space for the target classes. We initialize the parameters of the target feature extractor with that of the source feature extractor. Note that at this point, there is a domain shift in the latent features between the target and the source samples. This shift must be minimized via adaptation. But how do we obtain a proxy for the source data? This is where the source Gaussian prototypes come into play. We sample proxy source features from these Gaussian prototypes. These features are projected to the target semantic space and back to the source feature space where they are sampled from. We call the modules FE and FD as domain projection networks. These act as a transit mechanism between the semantic spaces. Finally, we introduce a classifier GT to account for the novel target categories and reuse the source classifier GS for the shared classes. Note that the classifier GS is frozen during the adaptation and acts on the source semantic space that contains the Gaussian prototypes, whereas GT acts specifically on the target semantic space to recognize new classes. The class logics are obtained by concatenating the outputs of the two modules. To reliably train the domain projection networks, we ensure that the proxy source samples retain class discriminative information. This is done by incorporating a classification loss and a reconstruction loss on the proxy source samples. Next, to perform adaptation, we define learnable guides that aid in aligning the target clusters. We employ the centroids of the source Gaussian prototypes as the guides for the shared classes, while the one-shot target samples are used as the guides for the novel target classes. These guides are used to pseudo-label the target features through a nearest guide assignment. The adaptation loss then drives the target samples closer to their respective guides. Simultaneously, we define Gaussian prototypes using the pseudo-labeled target data and employ a log softmax loss to separate out target clusters. This improves the granularity of the semantic space. Finally, we enforce a cross-entropy loss on the confident pseudo-labeled target samples, thereby training the classifier for learning new target classes. To summarize, we learn a target-specific semantic space where adaptation is performed by gradually aligning the shared classes using the learnable guides and while separating out the target clusters. This improves the semantic granularity of the latent space and enables class-incremental domain adaptation. We compare against prior unsupervised domain adaptation and incremental learning works. UDA methods require access to source data during the model upgrade. These methods lose semantic granularity as they cluster all the target private samples into one class. This leads to a low target private accuracy. On the other hand, class incremental methods show better results on the target private classes, but their performance is limited due to their inability to address domain shift. As the proposed method effectively addresses both domain shift and incremental recognition, we find improved performance over prior methods. To summarize, we propose a novel domain adaptation paradigm that addresses class incremental learning in the presence of domain shift. In contrast to prior work, our method is aimed at preserving semantic granularity during the adaptation process. An effective strategy for foresighted source model training, in combination with a novel class incremental domain adaptation algorithm, make the method a viable choice for practical domain adaptation scenarios. Please refer to our paper for more details. Thank you.